My name is Haley Hollinshead. I'm a UIS student, and this is my first video depicting NMR analysis using proton NMR and carbon-13 NMR. Okay, so the first thing we're going to be looking at is proton NMR. And my first step here is calculating the hydrogen deficiency index. And the way I'm going to do this is by using the formula of maximum hydrogens in a molecule, which is going to be equal to 2n plus 2. So I see my molecular formula up here is going to be C5H10O. So 2n plus 2 means that my maximum amount of hydrogens in this would be 12. So I'm actually missing 2 hydrogens here, which means that I have a hydrogen deficiency index of 1. So this means I could either have either a double bond or a ring in this molecule. The next thing I'm looking at are the integration values, which can be located right here as I've written them in. So I have an integration value of 27, 40.2, 28.4, and 42.2. So what I'm going to do with these, I'm going to divide by the smallest integration value, and by multiplying them to get a whole number, I should be able to add them to get the number of hydrogens in my molecule. So that's 27 divided by 27 is 1. Right, 40.2 divided by 27 is approximately 1.5. 28.4 divided by 27 is approximately 1. And 42.2 divided by 27 is approximately 1.5. So if we multiply these all by 2 to make these 1.5s become whole numbers, we should get our number of protons in the molecule. So we have 2 here, 2. Multiply by 2, we get 3. Multiply by 2, we get 2 again. Multiply by 2, we get 3. And so if we add all these together, 2 plus 3 plus 2 plus 3, that gives us our 10 protons. And we've accounted for all of our protons using our integration numbers. So the next thing we're going to do is look at our peaks and consider the n+1 rule in order to determine how many protons are neighboring the proton showed by the peak. So I can see we have, for this one right here, we have 3 peaks, so that means that we have 2 neighboring protons here. For this one, right up here, it looks like we just have 1, so 1 big peak, which means we have 0 neighboring protons. Here we have, it looks like we have 1, 2, 3, 4, 5, 6. 6 peaks right here. So we're probably going to have around 5 neighboring protons. And then here we have 2, 3 again, so 2 neighboring protons. In addition, if we look at, let me get this. If we look at this first peak right here, this first set of peaks, that's in the 2.0 to 2.5 parts per million range, which is actually probably suggesting that these hydrogens are next to a carbonyl group. Alright, so I'm going to go ahead and make some more room over here so we can start drawing out what we think this, this molecule is going to look like. Okay. So we know we're going to draw a carbonyl group because this was shown by our first set of peaks over here, and this would also account for our oxygen in our formula. And we know that the oxygen is actually going to de-shield these protons over here, these CH2 protons. So we know that they're probably going to be right around here. So we can move on to our next peak, and we see that we have 3 protons, so we know that we're going to have a methyl group here, CH3, and we can see that we have 0 neighboring protons. And yet again we can see that these protons are above, they show above the 2.0 parts per million on our spectra, so we can assume that they are definitely getting de-shielded by our carbonyl. So that means that they're going to be over here. And this also makes sense because our N+1 rule shows that there should be no neighboring protons to these protons over here, and where I've placed them fits this description. So let's move on to our next signal, and we have 2 protons, which is another CH2 group, and it looks like it's going to have 5 neighboring protons. But let's move ahead to our next signal, which we have 3 protons, which gives us a CH3 group, and it looks like we have 2 neighboring protons. And because we see that this signal here is falling under 1.0 parts per million, so we know that this one's going to be the farthest from our carbonyl, and that it is de-shielded the least out of the other protons. So I'm going to go ahead and draw that one in the farthest away. And then this makes sense because then our other protons that we just kind of skipped over a second ago right here, that means that they would fit perfectly right in this spot. Right, so, and if we look there, that means that these 2 protons do have 5 neighboring protons. And they fall right here. So we have 1, 2, 3, 4, and 5. So that accounts for our 5 neighboring protons. So this has been our proton NMR analysis of C5H10O, and now we're going to go ahead and look at our carbon-13 NMR analysis. So this is our spectra when we're examining the carbon-13 NMR, and right from the start I can go ahead and see from the number of peaks that I have that we're going to have different carbon environments. So it looks like I have 1, 2, 3, 4, 5 peaks, which means that I'm going to have 5 different carbon environments. So let's go ahead and draw the molecule that we drew on the other page according to our proton NMR. So 1, 2, 3, 4, 5. And then we had a ketone here, and then the rest surrounded by hydrogens. So we can see here then by these 5 peaks, we can pretty much assume that each of these carbons, we have 5, 1, 2, 3, 4, 5, we can assume that they're all in different environments then, signified by each of these peaks here. And then also, right here, we can see that this peak falls in the 220 to 180 range. And that's a good sign that we've drawn this molecule pretty accurately because signifiers in this range usually show a ketone or aldehyde, but in our case we see that we have a ketone. So this is a good sign that we've drawn this correctly actually. It's also pretty clear that we definitely don't have an aromatic molecule, because if we did, we would have spectra falling between around the 140 to 100 parts per million range, and it's pretty clear that we don't have any signals in this range. And it's pretty clear over here that these carbons all fall within the range of sp3 hybridized orbitals. So that's going to pretty much be the other carbons in our molecule that we've drawn. So here, 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 and here. So this has been my proton NMR and carbon-13 NMR analysis of C5H10O. And this is the final structure we have drawn that shows the different spectra and fits the spectra that we've examined in this video. Thank you.